Hey, how's it going? We got another question today, which is 9-ary tree order level traversal, which is a medium. Given a 9-ary tree, return the level order traversal of its nodes values. So a level order traversal, we have level 0 here in this example. We have, oh, actually, let me rewrite that. Looks like level 10. Level 0, level 1, level 2, level 3, and level 4. And you see with this question that the levels I've drawn out correspond with the output. So we have 1 for level 1, 2, 3, 4, 5 for level 2, 6, 7, 8, 9, 10 for level 3, and so on and so forth. So for this question, we want to do a breadth first search. What is a breadth first search and why is it a lot better than the alternative, which is the depth first search? Breadth first search would look at each of the children before going any deeper. So for 1, you look at 1, for you look at each of his children. So you look at 2, then you look at 3, then you look at 4, and then you look at 5. The depth first search, on the other hand, would do something different. Look at like 2, then look at 3, then look at 6, then look at 7, 11, 14, before you look at 4 or 5. And this becomes more of a headache for us because we want to do a level order traversal and look at all of these children at once. So let's start with our initial value in some data structure, which is 1. We know from this value we know the length of the first row is 1. So row length is equal to 1. We could pop this value out and have our first level have the value 1, which is correct. Then we want to add in all of its children, which are 2, 3, 4, 5, 6. Oh wait, 2, 3, 4, and 5. And we want to keep track of the row length here as well. Row length is equal to 4. Why do we want to keep track of this? Is because we're going to be adding the children to this data structure as well. So let's see. So first we would pop out 2, add to our output, and add in 2's children. 2 doesn't have any non-null children. Then we look at 3, pop it out, add to our output, add its children, which are 6 and 7. Then we pop out 4, add in its children, which are 8. Oh, my mistake. We want to add 4 here, add 8 over here. Then pop out 5 and add its children, which are 9 and 10. So having that row length stored from before tells us when to stop. So it tells us to stop after 4 values because these 4 values are in the row and the rest are all children. So then for our next iteration of this process, we have 6, 7, 8, 9, and 10 in an array. We basically do the exact same thing, which is store a row length equal to 5, pop them out, and add them to our output array while adding in their children. 6 doesn't have any children. Add it in, add 7, pop it out, add its children in 11, 8, pop it out, add it in, add their children. Pop it out, add it in, add their children, which is 13. And 10 doesn't have any children, so you just add it in. There we go. And we stop at 5 because we know there's 5 values. If we continue this process, we'll just be filling and emptying this data structure until we eventually get to popping out 11, 12, and 13, giving us the data structure with just 14, popping that out, and getting our final list. So 11, 12, 13, and then 14, which is our expected answer right here. So what data structure should we be using for this problem? So let's look at it from the beginning. When we pushed in 2, 3, 4, and 5, we want to look at 2, then 3, then 4, and then 5 before worrying about any of the children here, right? And the order we pushed them in was 2, then 3, then 4, then 5, because we looked at 1's children, which was first 2, then 3, then 4, then 5. So we have first in, first out. So this has to be a queue. It doesn't have to be a queue, like don't get me wrong, you can use an array, but for simplicity's sake, you can use a queue because you can just pop out the first value that you added in. So with this first in first out structure, all we have to do is start with the queue having the root value, pop it out, add its children, like we did here, and continue this process until the queue is empty, because we'll reach 14, it doesn't have any children to add in, and that's the last level that we're reaching. So with that being said, let's look at the time and space complexity for this question. The time complexity, we're looking at n is equal to the number of nodes. And we're going over all the nodes, so this time complexity is O of n. Space complexity, on the other hand, would be less than or equal to O of n, because the maximum space would be a fully fleshed out tree. The last row of values, which are these ones, 4, and a tree with 7. So we can do the math to figure this out in terms of height. It's probably some factor of height, 2 to the power of h. So it's probably O of h. I don't really want to do the math right now, but that's the time and space complexity generally. So we can look at some code so you guys can get a better understanding of the problem. Here we have my solution. If the root is null, we don't do anything, we just return empty. And we just add the root to our queue otherwise, and while the queue isn't empty, we run this process where we store the number of values in the current row, add the values in the current row, and add their children to a queue, and continue this process until eventually we have run out of values and we can return our output. This works fine, and this is the most optimal solution. So thank you guys so much for watching. The code is always in the description. Make sure to like, comment, subscribe. It means a lot if you could upvote the problem, or upvote my solution on Leetcode, because the answer will always be in the description. So if you have any friends that are worried about algorithms or studying for interviews, make sure you share this with them. Like, comment, subscribe, and I'll see you guys in the next video. Thanks.